Okay, the next thing we want to talk about is eigenvalues and eigenvectors. So eigen is German for characteristic. So these are characteristic values and characteristic vectors that are associated with a particular matrix. We're going to use this concept an awful lot, but we're not going to calculate it in very complicated circumstances very often. Instead, we're just going to stick to the 2x2 case, where it's pretty easy just to write down what the outcome is. So what a eigenvalue equation is it's a special equation that relates the matrix times a particular vector to be equal to a scalar value times a vector. So what this means is that for that particular vector, the matrix operating on that particular vector doesn't reshuffle the components of the vector, but just scales them up or down, just like you would multiply each component of the vector by a constant. So what do we have to do to get there? It's not obvious that that is going to be true, that it even possibly exists, but in fact it does exist for all matrices that will have eigenvectors and eigenvalues, and you can find them. And in the simplest case, which is the case that we're going to talk to here, the simplest non-trivial case is the 2x2 case. The 1x1 case is really easy because the matrix is already just a scalar single value. So so the matrix itself is its own eigenvalue. But for a 2x2, the matrix is not an eigenvalue is not equivalent to a scalar. It has two particular eigenvalues and two particular eigenvectors, because for this to be true, both the vector has to be special and the value has to be special. So for our standard 2x2 matrix, A, B, C, D, for that times a vector, V1, V2, to be equal to a scalar, just a number, times that vector, which is the same thing as saying lambda V1, lambda V2. If we wanted that to be the case, then this is the answer that we could plug in to make that work. The first eigenvalue is 1/2 A plus D minus a complicated quotient here, which I've written as Q, which is the square root of A minus D squared plus 4BC. It looks sort of like the quadratic formula. Not quite the same, so be careful. And then the other eigenvalue is A plus D plus Q. So minus Q and plus Q, so they're different by just the sign of this funny Q factor. And then along with this lambda is a particular vector, which I've written as A minus D minus Q over 2C, and 1 in the second row. And then the eigenvector that goes along with this eigenvalue is A minus D plus Q instead of minus Q over 2C, and then 1. And notice I've only written proportional to instead of equals to. Because if this is true for one vector, since this is a linear operation, I could multiply this vector by any constant factor I want, or indeed add it to itself, or add these two vectors together, and it should still work to be almost the same form, with the matrix distributing out over that operation, and any constant factor getting pulled out front, any sum being the matrix acting on the part that's proportional to the first vector, and then the matrix acting on the second part proportional to the second vector. Then it would be lambda 1, the first eigenvalue, times the first eigenvector, plus lambda 2, second eigenvalue, times the second eigenvector. Okay, in a second, we're going to have a discussion about how you might go about finding this and how to think about this in terms of matrix equations.